What we would be interested in to show is the following thing for our example. Whenever we have an output history y from this component which I specified, of course it has to fulfill the specification which is here. But if I in addition assume strong causality, I'm able to prove what I've written here. And maybe I should first read it for you. It says that whenever I have an output history of TMC, and TMC is strongly causal, then for all time points I have the following. If I look at any message, the number of occurrences of this message in the output until time t plus 1 should be at most the same or less than the number of messages in x until time point t. And which is, by the way, exactly a rephrasing of causality in a particular way. And now, how do we prove it? This is just strong causality, just copied from the definition. And how do we do the proof? It's very simple. We take a set, which is actually this set, and we choose a set with a property that set with this arrow, which means from t on, there are no messages there. And since causality says, in that case, we have this property. And then, of course, we know that having this property, then the number of messages in y has to be less than this according to this rule. And this just a proof. And so it shows that causality just says we do not see messages in the output before we have seen them in the input. And since we had some discussion in the coffee break on that, of course we could leave away the +1 here. Then we have only weak causality or straightforward causality. And what does it mean? We lose the +1 here. All other things remain the same. It means that we can have output in the same time interval as the input. So we can react to certain input at the same time interval.
Question. Do you assume that your inputs and outputs are prefix closed in some sense? Or?
No.
So I still don't see why this is not causal.
You shouldn't say prefix closed because I just consider infinite outputs. Right. And so prefix closed, you could generalize it to a way where you consider finite outputs, and then you could use prefix closure, and then you get into a lot of interesting theoretical questions. But to keep it simple, I just assume.
So could you explain once again why this is not causal?
Because it does not fit. This is the proof. This is the proof, because now you are in a situation where you can cut off this thing here, right, which means t is 3. And which means that if t is 3, you get 0 input here. This means if you choose a set like here, you get a set which will have not any input. Which means that if this is the same, you have to have an output here which has no input according to this. No output according to this. Because this says, if you put set here, no input, no output. And this means, since these two things have to be the same, it has to apply not only for z but also for x. And this is just nothing which fulfills what we have proved. Okay? It looks a bit tricky, but you can formulate it as a proof rule in a straightforward way, and then you can use it. This is basically the idea of the proof rule. So causality is nice and powerful, and it has a number of advantages, and I will show you one advantage in a minute. We talked about timing. This is a slide for you, which was already there. That didn't produce it. And it just says, if you are interested in timing, we have to write it down. And here you have a timing constraint. And the timing constraint says, let's assume we have a delay and we have a deadline. Delay says, if I send a message, the delay tells you how long it will take until you may receive the input the first time. And the deadline says, this is a guarantee, I will receive it at least at that time. And you can do it like introducing just the notation as I did. So for each message we require that the number of copies of the message in y until t plus delay is t plus delay, I should say. This is at a later point of view, is less than the message you have in x until t, which means that a message can, which is there, if you get an additional one, it can only show up after the delay. And if there's a message later than t, it can only show up after the delay. And here I say that the number of messages in y at a time t plus delay plus deadline is larger than x, the messages in x. So it means it's guaranteed to show up after we have seen the deadline. And so you can introduce timing properties. Of course, you can discuss whether this is a notation which is easy to deal with. And of course, you can think about a special notation for that. And we did. But since I don't want to go into this notational issue, I don't introduce it here. One interesting idea would also be to introduce linear time logic for that. That could be also help to express some of the properties. But what I wanted to show is this is just predicate logic. And you can have featured predicate logics like temporal logic to express certain things in a more readable style, fine. But here in my lecture, I'm only interested to show you the expressive power of that. So we can express timing properties, straightforward, okay? Now I go a step which I will not go into too deeper, just to show you how to extend the model. And the first thing is probabilistic systems. You have seen the explanation of CPS. And of course, if you look at CPS, you immediately realize that in many situations you are interested to study probabilistic systems. One example would be functional safety, which I have to be careful, is different from how safety is defined in theoretical computer science. Functional safety is concerned with the question whether we can produce systems which do not do harm to people. And if you do that, of course, since people know that you will never be able to produce perfect systems, then you think about what is a probability that something could go wrong. And just to give you an example, in many cases, if systems operate in critical situations, you would assume that the probability that something could go wrong is below 10 to the minus 9, for instance. But if you want to do that, of course, you need system models which talk about probability. And let's now do that. I can just go back to my simple example and say, well, for some reasons, I do not assume that I have such a perfect system. And we know that our mail systems are also not completely perfect. And now the question is, what would be a good quality issue? And now we are also in the area of quality of service. And I give you just a very, very stupid example to give you the idea. So what I would like to do is I would like to introduce probabilities. And this would be a probability saying that the probability that a certain property is fulfilled, which is just the timing property, or part of the timing property, so that I see all my input after I have reached the deadline is better than 80%. Now, let's now think about how can we introduce that in our system model. And now I show you how we can extend the system model. And this is work one of my PhD students did. He said he had the idea, or we had the idea, and he worked out all the details, to use exactly the same model I've shown you, but you just add one little thing. Here we have a set of outputs for each input history. And now you introduce a probability distribution for that. And this is also something which I can explain with a story. A typical application area for models like that would be telecommunication. And if you have a telephone, of course, it's in many cases the telephone will not work perfectly. So if you put on the hook, you would be interesting to get a kind of a connecting tone. But of course, we know also that sometimes telephones are broken and you don't get this connection tone. If you work with the model which I've introduced so far, what you could just do is say that the telephone is non-deterministic. If I put off the hook, which is input to the telephone, by the way, the result could be that I get the connection tone, but it could also be that I don't get a tone. And if I write it down in a deterministic way, both would be as good. And if you follow the idea of refinement, as you find it in many approaches to non-deterministic system, then a refinement that refines the telephone into a telephone where you always do not get the connection tone would be perfect from a formal point of view. But of course, nobody would like to have such a development. Therefore, it would be an interesting idea to say, well, to make sure that I go the right direction, I say this in a probabilistic way, and I say that I get the connection tone with a probability of 0.9 or 0.99. And this can be expressed here by just introducing a probability distribution, because roughly speaking, now you get for all the possible output histories you can get for one input history a probability. It's not exactly true, because probabilistic theory is a little bit more complicated. And if you go into a finite space, of course, you cannot get a probability for just one element there. So you get a probability distribution which gives you probabilities for so-called measurable sets. And I will not go into that. This is all worked out in this PhD thesis by my student, Philipp Neubeck, who wrote a really wonderful thesis 5 years ago on the probabilistic theory of interactive systems. And I was really wishing that he would continue. And what did he do? He went to Google. Bad luck. Anyway, what he produced as a result is still a very nice one, because what I was interested in, and that was the basic idea of the thesis, is that we take the system model as we have it and put probabilities on top of it without changing anything in the model we had so far. And this was possible, and this worked out. And therefore, in a certain sense, you can use the model I've introduced so far, and having a non-deterministic specification, you could decide, now I'm interested in probabilities, and I add probabilities. And by the way, with the timing, it's the same. I gave you a specification which was not talking about time, and you could decide, well, I'm interested in timing, and you add timing. And if you're interested in probabilities, you can add probabilities. But then really to work with probability is not so easy. And what we did not do, I have to say that, we did not work out a more pragmatic approach to that. So there's a lot to do in addition. The thesis just proves that it is possible. By the way, what we looked at is what happens if you do that. And this leads to a number of very interesting additional discussions. First of all, if you add timing to system behavior, then time is a functional behavior of a system. And if you look at the standards, in particular the IEEE standards, a lot of the standards say timing is a non-functional property. And I just say this is wrong. For cyber-physical system, time is a functional property. And if you consider models with probability, and you say probability is part of the functional properties of a system, and I would claim for a telephone, the question, what is the probability that you get a connection tone, is part of the functional behavior of the telephone, then suddenly other so-called non-functional properties become functional. For instance, reliability becomes a functional property. So I think if we do that in a proper way, we have to really rethink a number of the categorizations of those properties in systems, but this is a different story. So I just wanted to show you we can deal with probabilities, and so we get a probabilistic view for the interface behavior, and we will not go into deeper, but I can also extend it to the architectural view and to the state view. And so, as I said, the model covers then certain so-called non-functional properties like safety and reliability, and we could also do a functional definition of integrated fault trees. As I said, Neuberg worked on that. But now I will leave this idea of probabilistic things and will go to architecture and state. So far we have only treated the interface view, and if you think back on my definition, we have covered this, but now we will cover that. The structuring of system in subsystems and in state and state transitions. And now we first talk about a key issue, which is composition and decomposition. When we work with cyber-physical systems, a typical thing is that you put together a large complex of a large system by a number of smaller subsystems. And of course, then we have to be able to do composition. And I will not introduce composition at the level of the mathematical system model, and perhaps I should emphasize actually, I have introduced a mathematical system model, which was this function that maps histories, input histories onto sets of output histories. But I do this only at the equivalent idea of specifications. So I consider two specifications, and I do that only for the simplest case by composing two subsystems. But it can be generalized to arbitrary numbers of systems. So I have a subsystem F1 and a subsystems F2. Both have input and output channels. And to keep it simple, I assume that each of the systems, like F1, has one input channel which is different to all the other input channels. And it has an input channel which maps exactly with an output channel of the second system. And vice versa, it has a separate output channel, which is this one, and it has an output channel which maps exactly with the output channel of the other system. So we do the matching of the channels just by choosing the same names. Of course, you could think about a more sophisticated way of composing systems, but this is not difficult to do by a kind of renaming of channels and so on. So to keep it simple, I say, if we put together two systems, they can be put together if their joint input and output channels match according to their data types and according to the direction. So input match with output channels and so on. And now we can put together the two systems and we get a composed system. In this composed system, these two channels here are used for communication. So they are no longer visible to the outside, and I get a new system which is very similar to the old systems where I have two inputs, x1 and x2, and two outputs, y1 and y2, which is exactly here. And now the key is, what is the formula which describes the composition of the two systems? And it's very, very straightforward. It is a logical expression which uses these channel names as identifiers for streams. So the assertion I get here is there exist streams for these internal channels Z12, Z21, such that both S1 and S2 holds. And this is something we, I think, worked out in the 90s. And I was very, very interested to have a formula which is as simple as that. Parallel composition is logical and channel hiding is existential quantification. So you have a very direct relationship between what's going on at the system composition level and what's going on at the logic. And I don't give you the proofs, but it's not too difficult to prove that if you do an operational semantics for the descriptions here. What you get here is a valid proof theory. And now let's come back to causality. It's a valid proof theory in any case. It's a valid proof theory also for weak causal systems. But for weak causal systems, this is not a complete proof theory. And the reason is that for weakly causal systems, you have fixed points here. And for weak causal systems, there's no way, and it's true what I say, there's no way in general to characterize least fixed points. So you get non-causal fixed points. And non-causal fixed points can be explained as follows. Assume you have a friend, and you and your friend have some trouble to each other. And so you have to expect an excuse from your friend. And if you get an excuse from your friend, you are good again with him. And your friend expects the same. What will happen? You are waiting for a message from your friend is waiting for a message from you. What will happen? You will wait forever. It's quite clear. Now, if there's a little demon who assumes that you got a message from your friend and makes you believe that this is true, and as a result you send a message to your friend says, oh, I got a message from my friend, and now I'm in a good relationship again, so I send my message. It's exactly happening also the same. Both got messages from each other and answers to that, because getting positive messages, they answer by positive messages. So the specification is fulfilled. But it's fulfilled in a weird way, which is not realistic, because it's non-causal. This waiting for the message of a friend and only replying if there is one is exactly related to causality. And if you have weakly causal models, you cannot distinguish a causal behavior from a non-causal behavior. And if you look at Esterel, Gerard Barry does a lot of stuff just to make sure that he gets rid of some of the non-causal behaviors. If you have strong causalities, this problem disappears. Because in strong causality, we can show that what we get here is exactly a complete proof theory for our systems, assuming that we can prove predicate logic. Okay? So strong causality allows you to control feedback loops in a way that everything works out nicely. Okay? So you can form architectures. So you have now this composition. By the way, I denote putting together two systems in such a composition by this circle with a cross in it. That's a composition operator. And so I have here now 3 components which I compose into one system F, which looks like this. And if I do so, I get a new behavior, which is exactly what is described by this composition operator. And this new behavior, the internal channels disappear, and I get exactly a behavior which is only describing the relationship in terms of an interface assertion to the outside. And forming architectures now is very nicely done as follows. We get the architectural behavior here, which is basically the description of the function which defines the behavior. We can also get the architectural spec. The architectural spec, by the way, also talks about the properties you find for the internal channels. And architectural correctness is now having the properties of the subsystems. And as I showed you, a logical end is good enough, and I can get rid of the existential quantification because it doesn't matter here a lot. You have to be able to prove from this the original system specification for this. Maybe I should go back to for this overall system. So, and I will come back to that a little bit later. Using this approach, you can prove architecture is correct by just looking at the interface description of the subsystems. And this is a key, because it is a key to abstraction, and to what is a result is modularity. And now we come to an interesting question. What is the formal definition of modularity? What is the formal definition of modularity? And I give you mine. For me, the formal definition of modularity is as follows. A system engineering approach is modular if we can derive the behavior of a composed systems, or more precisely, the specification of the behavior of a composed systems in a valid way from the specifications of the subsystems. And this is exactly what happens here. Modularity means, given the specification of the subsystems, we can derive from this the specification of the composed system. So for a strongly causal system, this approach is modular, and even more, it is complete with respect to the properties that are described that way. And this is a key. If you don't have that, you get into troubles, because it means that there are properties of a composed system that cannot be derived from the properties of the subsystems. And that means that all the abstraction mechanisms we have introduced are not good enough. Okay? That's a key. Yeah?
For the property, the specification is a logical AND.
Mm-hmm.
For the interfaces, it looks like to me logical OR. So when the data types are different, how do we compose?
I did not completely understand your question.
The data types are same.
Yeah.
So when you compose...
If you would have different data types for, say, set 2-1 and set 2-1 here, you cannot compose. I did not give you the rules explicitly, but the rules say you can compose only systems where their channel names match in a consistent way.
So for the data, it is more of a logical OR. So if the data types matches, you just take all the data. Because the specification talks about logical AND, I understand.
Yeah, that's for sure. I'm not sure whether I really would accept that it's a logical OR. It just means looking at two systems, you look at the channels. There are channels which are in F1 but do not occur in F2, X1. Say stay. Yeah. There are channels which occur in F1 and in a consistent way. Consistent means same data type. Here it's input, here it's output. Yeah. And they are combined and disappear because they are internal. Yeah. So it's not really logical OR. If you would like it in logical terms, which I don't think I would like to do, it would be exclusive OR. And they match, and you can put together systems only where their components, where their channels match. And if channels match, it's exclusive OR. Other questions? Okay. So the next step would be, for instance, if we specify a car's architecture, then I just wanted to show you, and this is very similar to what we just heard in the last lecture, we also have to talk about assumptions. And now we can already talk about assumptions. What are assumptions? These are assumptions about the context in which we go into a system. So for a car, we would like to have a rule which makes sure that if the doors are not closed, the actual speed of the car is 0. So it means the car never moves if the doors are not closed. That would be an this is not true for a lot of cars we have today. It might not be a good idea for cars in the end, because sometimes people would like to move cars even if doors are open. But to keep it simple, let's assume we are interested in such a property. And now we have a car with a motor. This basically is the cyber-physical system which controls the motor. And we have a watchdog which is responsible for this rule. And now we can look at the watchdog and we can just take what we have here. Doors are not closed. What we would like to have, that actual speed is 0, but we cannot do that because this watchdog can just send messages to the motor, and the motor determines the actual speed. So what the watchdog can just do, he can just determine the output which is here. So this is the only possibility of the watchdog to say something about this, influencing hopefully the speed. But of course we need an additional rule for the motor. The motor says if it gets the message not ready, then it makes sure that the actual speed is 0. And now if we put those things together, according to the rules I gave to you, we can conclude from that this is this rule for the general system. So this shows you how properties of the components are put together finally to end up with the property you see here. And this is typical for the architecture of systems. You look at sub-properties, and now looking at this simple example, you can look at it from two sides, top-down or bottom-up. If you go top-down, and this is how I introduced it, you have two components, the motor and the watchdog. You have a certain specification for the car you want to achieve, and you derive from that a rule for the watchdog and a rule for the motor. Another possibility is to do it bottom-up, and you say, I have two specifications for the watchdog and the motor, and I put them together, and I get this specification for the car. What is important with this example is that it shows that you can use this rule of composition, which I've introduced top-down or bottom-up. It just tells you how you can derive from subcomponents system behavior, and it tells you indirectly how you can decompose system behavior into assertion for subcomponents. Okay? And this is another key issue in system design: decomposition and composition. Decomposition top-down, composition bottom-up. Okay? Questions?
One question. You introduced before the idea of adding also probability. Does this modularity hold also when you add probability? Or?
Yeah, that's a good story. The answer is yes. I will not show it to you because this is really needs more details. But in the thesis, my PhD student proved that this rule carries over to, if I have a probabilistic specification here and a probabilistic specification here, I get a probabilistic specification for the composed system. So this was the property I was most interested in, and this was a nice result of the thesis that it really turned out to be true. And that's important. Okay. The next thing is, I guess, closer to what you are familiar with. I will now show you that you can relate what I did also to state machines. And there is another aspect which I want to emphasize here, because the state machine stuff is more straightforward. Another thing which I want to emphasize here is related to UML or SysML. Who of you knows UML? Who knows SysML? UML and SysML is used to a certain extent today in practice, and it has a number of disadvantages. One of the disadvantages is that it does not have an accepted semantic model, so you really cannot properly talk about behavior. It does not have a real accepted specification formalism, also not one which is proved to be valid and correct. And the third thing, which I think is most critical, is that in UML, it's not clear how certain sub modeling approaches fit together. So if you take, for instance, a class diagram and a state chart, it's completely unclear how the class diagram and the state charts fit together, whether they are consistent or not. What we are very much interested in this approach to have what we call semantic coherence, and I will show you what I mean by that. And this is why I introduce systems and states. Systems have states. A state is an element of a state space. For practical reasons, we characterize state space by state attributes. For instance, we say we have a state space of 3 attributes x1, x2, x3, which are variables of type real. Or we could say in a cruise control, speed, set speed are real variables, engine on, activated are Boolean variables, and so on. So it's a straightforward way. And this relates again to what we discussed this morning, how data are used in states. And now having state spaces, and I consider the state spaces denoted by sigma, which is a set of states. Each stage is an evaluation of all the state attributes. And we have a set of initial states. We can have a state transition function. And here I just explained the state transition function, and this is just an example how you could introduce some graphical notation to define states. And I will not go into that. I just will explain the state machines we consider. We consider state machines which a state transition function. They are given a state and given an evaluation of the input channels. But now an evaluation of the input channel is not a stream. It's just a sequence of messages. And that is related to what I said. In each time interval, you get on each channel a sequence of messages, which can be empty, which can be one message, it can be many. A subsystem would be, sub-idea would be that we say only empty or one element. So you have a lot of possibilities to have variations on that. So given the state and this evaluation of the input channels, the state transition gives you a set of pairs of successor states and evaluation of the output channels with a set of messages. That's the whole idea. And here there is a paper where this is done in more detail. So in general, we have these state space, a set of initial state, this transition function. So it's just a special case of, and you are hopefully familiar with that, of a Mealy machine, right? It's a special Mealy machine. What is special? The special thing is that the input and output that I have here is related to these channels, evaluation of the channels. Yeah?
So this was a probability for the output?
Sorry?
It's in here like a math count P?
This?
Yeah.
This is power set.
Oh, okay.
So you get a set of pairs, okay? And having this, now I can define for a state, yeah?
So you said that it's a Mealy machine, but I thought that Mealy machine, the output depends directly from the input one.
Absolutely right. We talk about causality in a second, okay? I just introduce it in the full generality. And now given a initial state and a sequence of inputs, and a sequence of inputs actually is a stream. Because this is a sequence, this is a sequence, this is a sequence, and if we take an infinite sequence of those, we get back to our streams. And we get a sequence of states and a sequence of outputs according to this formula. We take the ice state and the ice plus 1 input. This starts with 0, this starts with 1. And from that, we get a set of pairs. And then we can take one of those pairs, which is a state, and the valuation of the output channels. So We get a straightforward computation that way, and this allows us to associate with such a state machine a behavior. I just wrote down now the computation in a style which is more common. Initial state, first input, first output, next state, second input, second output, second state, and so on. So we get such a computation, if you like. And if we abstract from the computation, given the inputs, just the outputs, we come back to our behavior. So this shows an interesting observation, which each of these Mealy machines we can associate exactly a behavior in the terms we have introduced it. So Mealy machines defines an interface behavior. That's all I say here. And I call this the abstraction of a state machine, because now we just take all possible initial states for an input, and we get a set of possible outputs. So for a general Mealy machine, by this abstraction, we get an interface behavior. And now I come back to your question. A Mealy machine usually is in a way that what we get as output here may depend on the state we are currently considering. And so it's not strongly causal. But we can also switch to a Moore machine. And the Moore machine has a property that the output only depends on the state, not on the input. And therefore you get, if you produce new input, you can see reactions to the input only a step later. And this is exactly strong causality. So this, only not giving you the formal proof, but giving you the proof idea, shows that a Mealy machine produces behaviors that are weakly causal, and Moore machines produce behavior that are strongly causal. Full stop. Okay? Does that answer your remark? And now we can use state machines by constructing them, specify the syntactic interface, specify the interface behavior. You could do it by a state interface assertion. That's a specification. Construction, construct the state space, define the attributes and the data types, define the state transition, choose control states and state transition, label state transition diagrams, verification, prove that the state machine shows a specified interface behavior. So this type of state machines is exactly coherent with the interface definition which I have introduced in the beginning. And now we can do interface abstraction for state machines. Given the state machines with a syntactic interface and its interface behavior, we can call the step from the state machine to its interface the interface abstraction. And of course, it's interesting then to think about verifications. I wrote a paper on that too. And now we get something which is very interesting. When we have two system models, modeled by state machines, we can ask whether these state machines are observable equivalent. And this is the case if their abstractions are the same. And it's obvious that you can, for a given interface behavior, you can construct a lot of different state spaces with the same interface behavior. And now here the conclusion on system with state machines. Each state machine defines an interface behavior. Each interface behavior represents a state machine. I should be more precise. Each causal interface behavior can be, for each can be constructed a state machine. And for each strongly causal interface behavior, we can construct a Moore machine. Machines can be described in several ways, mathematically, graphically, state transition tables, programs. State machines define a kind of operational semantics. So if you have a state machines, you are close to an implementation usually. Systems given by state machines can be simulated. From state machines we can generate code, what we do. And from state machines we can generate test cases. So state machines is a step into implementation. Finally, I will not go into this. I can introduce also a composition operator on two state machines. Parallel composition of two state machines gives a composed state machine. By the way, it's interesting, if you would assume that these are Mealy machines, this would not be a consistent definition. And my claim is there is not a consistent definition of parallel composition of Mealy machines along those lines, but for Mu machines it's consistent, because you don't get into contradictions with respect to the constructed states. But I will not go into details. If you're interested, I said I will send you the slides and you can look at it. Now, I will conclude with this property, which I consider as a key property. A key property from a practical point of view. And what does it say? It says the following. Given two systems, and you can think about many systems, but I just do it for two systems which are described by state machines. System 1 and system 2. I can do a parallel composition of the two state machines and I get a state machine. It's a composed state machine, and I showed you the definition, but I didn't explain it to you. And then I can do the interface abstraction. And I give an interface behavior of the composed state machine. This rule says that you get the same if you do the interface abstraction for the both state machines and then do the composition at the level of interfaces. Why is this an important property? Yeah, it's another version of modularity. As an engineer, it's no difference whether you work at the level of state machines and does all your work there, or you rather abstract. So you can always abstract from the state machines and forget about details of the state machines and only consider the interface behavior, which usually should be much simpler than the state machine, and then argue on composition at the level of interfaces. And it's up to you as an engineer to choose it. In UML, you cannot even formulate this theorem. Whether it's valid is unclear because you cannot formulate it. And this is one of my claims. If you do a system theory for CPS, then the system theory has to show a number of properties which are of high engineering value. And you have these properties, you can do certain steps in engineering. If these are not true, they bring in a lot of additional problems or wouldn't allow you to do this in a very controlled way. And this is exactly the state of the art we have today. Because then you have to do a lot of stuff, and you do also such steps without knowing precisely, and I will talk about that a little bit more in detail at the end of my lecture. You are in the difficult situation that you are not sure about whether certain patterns of engineering are valid patterns of engineering, and you have to do much more proofs than you would have to do if you understand these rules. Yes?
Excuse me. Why you are using a logical OR instead of logical AND in this conclusion?
I'm sorry, this is not a logical OR. This is just parallel composition. Some people use it as logical OR too, I don't. Okay? Yeah, please. This is a rule which just holds for Moore machines. Okay. So it just holds for strong causality. Mm-hmm. For weak causality, it is not possible to formulate it because we cannot formulate parallel composition of Mealy machines. Mm-hmm. Okay, that's it. Thank you.